So this is the alpha beta algorithm then. Again, we're going to start at a state, but this time we have to specify two parameters, alpha and beta, for our max value function, which returns utility of a given node. So you have the input, the state, which is the current state of the game. Alpha is the value of the best alternative for max along the path that we've seen so far. And beta is the value for the best option for min along the path we've seen so far. And again, as long as the value is better or equal than beta, so that's the only change really is in determining the value of a function. We are constantly checking if the value is bigger than the minimum we have so far. We keep checking, otherwise we're done. We cut our investigation along that path. So pruning does not affect the final result. If we order the moves in a way to minimize the function evaluations, that can improve the effectiveness of pruning, obviously. And you can see that here, if the 2 was on the left before the 14 and the 5, we would have avoided evaluating both the 14 and the 5. So ordering the move can make a difference to speed up. If we have perfect ordering, then we're cutting the time complexity to b to the m over 2. And then, but it's still, for a game like chess, that would end up being 35 to the power 50, which is still impossible. Now let's look at our final approach, which is multi-colored tree search. So, like we saw, and with alpha pruning, the game is still, we can't really speed up the search enough, even with pruning, to find a solution in reasonable time. So, one alternative strategy is to use multi-colored tree search. Now, the multi-colored tree search strategy does not use an evaluation function. Instead, the value of a state is estimated as the average utility over a number of simulations of complete games starting from the given state. So a simulation, which some books call rollout or playout, chooses moves first for one player, then for another player, repeating until we reach a terminal state. At that point, the values of the game determine who has won or lost. So we don't cut the game early. We keep going with our simulation until we reach a terminal value. Now, for games in which there's only one outcome, win or lose, the average utility is the same as the win percentage. So out of 100 simulations from a given state, how many times did max win, or how many times did min win, and that gives us the average utility at that given state. Now, how do we choose then the move to make during this simulation? If we just choose randomly, then after multiple simulation, we get an answer to the question: what's the best moves if both players play randomly? To get useful information from the payout, we need a playout policy. Okay, so we can't just let them do random moves during the simulation. We have to use some kind of approach that biases the move towards good ones. For example, for the game of Go and other games, playout policies are learned from self-play by using neural networks, for example. Sometimes game-specific heuristics are used, such as consider capture move in chess, for example. So given a playout policy, we next need to decide two things. From what position do we start this simulation? and how many simulations are we going to perform at each position. So the simplest answer, which is called pure Monte Carlo search, is to do n simulations from the current state of the game and track which of the possible moves from the current position has the highest win percent. Okay, so that would be our move in that case. Now, for some stochastic games, this converges to optimal play as n increases. So as we increase the simulation, this will eventually give us the optimal strategy. But for most games, this is not enough. So we need a selection policy that focuses on the important parts of the tree game. So it's going to have to balance between two things: exploration of states that have had few simulations, and exploitation of states that have done well in past simulation to get more accurate estimate of their value. So Monte Carlo tree search does that by maintaining the search tree and growing it on each iteration of the following 4 steps. So let's look at the specific steps and then we apply them to an example here. So step number 1 is the selection. So starting at the root of the search tree, we choose a move which leads to a successor node and repeat the process as we go down the tree. So in this case, for example, we started here, we performed simulations. We found that the highest percentage win is 60 out of 79. So this is where we need to go next. And then at this tree, we found 2 possible actions. If we move to this direction, we only get 3 out of 26 simulations as winners. In this one, we end up 16 out of 53, so we're going to move down this way. And then finally here, we see that again, the average win percent here is 27 out of 35, which is higher than 10 over 18. So we're going to go down this way. So this is called the selection. So start at the root, choose move, and then repeat moving down the tree. Then we have expansion. We grow the tree by generating a new child of the selected node. Okay, so this is expansion right here. So you can see that since we ended up at this point, we're gonna grow a new child here. And then the next step is simulation. We perform a simulation from the newly generated child node, this child node right here, choosing moves for both players according to the playout policy. These moves are not recorded in the search tree. And then back propagation. That's the final step. Is we now use the result of the simulation to update all the search trees. So all the nodes along the tree, all the way to the root. Since black 1 here, so in this child right here, black 1, so this one goes from 27 out of 35 to 28 win out of 36, which means this one This one lost in that case, which makes it 16 out of 54. This is a win for this guy, so 61 out of 80 instead of 60 out of 79. And then finally, it's a loss for this guy, so it becomes 37 out of 101. So this is the back propagation step. So we repeat these 4 steps for a set of iterations or until we run out of time, and then return the move with the highest number of winning simulations. Now, one very popular selection policy is called the upper confidence bound, which is applied to trees or UCT. Essentially, this policy ranks each possible move based on an upper confidence bound formula, which is shown right here. For node n, we say U of n, which is the total utility of all payout that went through node n, divided by n of n, which is the number of simulations that passed by node n, plus the square root of log n times parent of n, which is the parent of n in the tree, divided by n of n, which is again the number of simulations that passed by node n. This term right here is called the exploration term, and the average utility of n. That's what it represents. This has, as you can see, n of n in the denominator, which means the term will be high for nodes that have only been explored a few times. In the numerator, it has the log of the number of times we explored the parent of n. This means that if we're selecting n, to visit this node n a given percentage of time, the exploration terms goes to 0 as the counts increases. So as we revisit the same node over and over, there's nothing left to explore. So this entire term right here will become smaller, will eventually reach 0 if n, big N, reaches infinity. And if that's the case, then we're done exploring. There's no more exploration term in that case, and the utility of this node will be U of n over, which is the average utility over how many times we visited it.